Hi everyone, welcome to Education Hub Zone. So today we are going to discuss about organic chemistry, part of Introduction to Organic Chemistry. Before getting started, please don't forget to like, share and subscribe on my YouTube channel for more upcoming videos. Okay, let's get started. Organic chemistry is the branch of chemistry which deals with the study of compounds of carbon with hydrogen and its derivatives. Distinction between organic compounds and inorganic compounds. Organic compounds have low melting point and boiling point, while inorganic compounds have high melting point and boiling point. Organic compounds have low solubility or insoluble in water, but soluble in nonpolar solvents, while inorganic compounds have high solubility in water but insoluble in nonpolar solvents. Organic compounds are covalent compounds while inorganic compounds are ionic compounds. The organic compounds solution don't conduct electricity while the inorganic compound solution conduct electricity. Organic compounds are flammable while inorganic compounds are non-flammable. Organic compounds exhibit isomers while inorganic compounds don't have isomers. Organic chemical reactions are very slow while inorganic chemical reactions are very fast. Characteristics of carbon atom. Carbon forms a very large number of compounds. Why? Tetravalency of carbon. Carbon has tendency of forming 4 bonds. Ionization and electronegativity of carbon. First, ionization energy of carbon is very high. Also, the electronegativity of carbon is 2.5, neither too high nor too low. Therefore, carbon can neither lose nor gain electron to form ionic bond. Instead, carbon share its electron to form covalent bonds, tendency to form multiple pi bonds. For example, ethene. From the triple bond, 2 bonds are pi bond and 1 bond is sigma bond. Catenation is a tendency of atoms of the same elements to link themselves and form the longest chain. Carbon has large tendency of catenating. Types of hybridization of carbon. The sp3 hybridization of carbon. This is when carbon link with 4 atoms. Example, formation of methane. Carbon is linked with 4 hydrogens. The sp2 hybridization of carbon. This is when carbon link with 3 atoms. Example, formation of ethene. Each carbon is linked with 3 atoms. The sp hybridization. This is when carbon link with 2 atoms. Example, formation of ethane. Each carbon is linked with 2 atoms. Structural representation of organic compounds. Lewis structure, structural formula, condensed structural formula, bond line formula. Number 1. Lewis structure. Example, methane. In Lewis structure, the valency electron of each atom are represented either by dot or cross. Here, I choose dots to represent valency electrons of carbon and cross to represent valency electron of hydrogen. Structural formula. It shows how various atoms are linked to each other in a molecule at any compound. Example, methane. All bonds that are attached to carbon are shown clearly in this diagram. Number 3. Bond line structural formula. Bonds are represented by lines. Carbon atoms are represented by the line end and the line intersections. Hydrogens are assumed to be there to complete the number of bonds. Example, propane. So each end of the line contains carbon. So there are 3 carbon in propane. Butene. Each end of the line represents carbon. So there are 4 carbon with 1 double bond. Functional group is an atom or group of atoms which determine the chemical behavior of organic compound. Example, functional group is carboxylic group. Homologous series is a family of organic compounds which contain a functional characteristic group and exhibit similar properties. Characteristics of homologous series. All members of homologous series have the same functional group and can be represented by a common general formula. Each member of a homologous series differ from the next higher or lower member by a common difference. All members are or can be prepared by common general method of preparation. They exhibit similar chemical properties. Physical properties show regular change with increase in molecular mass. Typical homologous series: alkane, alkene, alkyne, haloalkane, alcohol, ether, amines, carboxylic acid, amide, ester, carbonyl compounds, acyl chloride, and acid anhydrides. Fission of covalent bonds. All organic reactions involve breaking or fission and making of covalent bonds. Organic reactions are chemical reactions involving organic compounds. A reaction mechanism explains how reactants become products. Types of bond cleavage. There are 2 types: homolytic bond cleavage, homolysis; heterolytic bond cleavage, heterolysis. Number 1. Heterolytic bond cleavage is a bond breaking between two bonded atoms having electronegative difference. The most electronegative atom will acquire both bonded electrons and the least electronegative atom will be deprived of electrons. This bond cleavage is represented by full arrow starting from the middle of the bond directing to the most electronegative atom. The arrow will start from the center of the AB bond and will direct electron to B, which will form A ion plus B ion. Heterolysis results into formation of ions nucleophile and electrophile. Nucleophile. They are nucleus-loving species. They are electron-donating species. They can be negatively charged species, anions. They can also be neutral species with lone pairs. Also any species with pi bond. They are electron-rich species. Electrophile. They are electron-loving species. They are electron-seeking species. They are electron-deficient or poor species. They can be positively charged species. They can be neutral species with vacant orbital. Number 2. Homolytic bond cleavage is a bond-breaking process in which each atom or group of atoms separates out with one electron from the bond electron pair. Homolytic bond cleavage results into formation of free radicals. Free radicals are electrically neutral species with unpaired electron. Principles of showing mechanism of organic reactions. Movement of electron is shown by a curved arrow. Tail start from the source of electron bond or nucleophile, and head should point to a point in a site where electrons shift to. If there is a homolytic bond cleavage, the movement of electrons will be from the bond to the atoms. Equal movements of electron also will be represented by a half-head curved arrow. For example, under UV light, each atom from bromine gas will acquire one electron from the bond to form free radicals. For heterolytic bond cleavage, full head curved arrow is shown. Consider this reaction. The chlorine will acquire both electrons from the carbon-chloride bond, and the carbon atom will become positive, and the chlorine will become negative. If a curved arrow starts from nucleophile site to electrophile site, it implies that there is a bond formation. If a compound acts like a nucleophile using its pi bond electron pair, the arrow will begin from the pi bond, pass the atom to which the coming electrophile attacks, and the atom deprived of pi bond electron pair is left positively charged. See this reaction. The carbon that is attacked by hydrogen will take both electrons from the double bond, and the carbon that is left will become positive. If a compound acts as a nucleophile using its lone pair, the arrow will start from lone pair towards electrophile, and the atom donated lone pair becomes positively charged. Types of organic reaction. The most common organic reactions are substitution reaction, addition reaction, elimination reaction, rearrangement reaction, and redox reaction. Substitution reaction is a type of organic reaction whereby one atom or group of atoms is replaced by another atom or group of atoms. Types of substitution reaction. Electrophilic substitution reaction is a type of organic reaction whereby an electrophile is replaced by another electrophile. Example, Friedel-Crafts reaction. The reaction between benzene and haloalkane under Lewis acid is an example of electrophilic substitution reaction whereby the alkyl group replaces side hydrogen from the benzene. Nucleophilic substitution reaction is a type of organic reaction whereby a nucleophile is replaced by another nucleophile. Example, from this reaction, chloride is replaced by hydroxyl group. Free radical substitution reaction is a type of organic reaction whereby a free radical is replaced by another free radical. From this reaction of methane and chlorine gas under UV light, hydrogen free radical is replaced by chlorine free radical. Number 2. Addition reactions is a type of organic reactions whereby an atom or group of atoms are added to an unsaturated organic molecule without removal of any atom. Electrophilic addition reaction is a type of organic reaction whereby an electrophile interfaces into unsaturated organic molecule followed by a nucleophile. See this reaction between alkene and hydrogen bromide, whereby hydrogen ion interfaces into the double bond followed by bromide ion to form a haloalkane. Nucleophilic addition reaction is a type of organic reaction whereby a nucleophile enters first into unsaturated organic molecule followed by an electrophile. See this reaction. Ketone react with hydrogen cyanide, whereby the nucleophile cyanide interfaced into ketone followed by the hydrogen. Rearrangement reaction is a type of organic reaction whereby organic molecule rearrange itself to form a product. See this reaction when ammonium cyanate is heated, it rearranges itself to form urea. Elimination reaction is the type of organic reaction whereby an atom is removed from organic molecule without addition of any atom to that organic molecule. See this reaction between alcohol and conc sulfuric acid at a temperature 170 degrees centigrade react to form alkene and water. Condensation reaction is a type of organic reaction whereby two or more organic molecules are added with the removal of small group. Consider this reaction. Two monosaccharides react together to form disaccharide with the removal of water. Redox reactions is a type of organic reaction that involves reduction and oxidation. Reduction is the addition of hydrogen or is the removal of oxygen. See this reaction. Aldehyde is reduced by reducing agent lithium aluminium hydride to form alkane. Oxidation is the removal of hydrogen or addition of oxygen. See this reaction. Aldehyde is oxidized by potassium permanganate to form carboxylic acid. Factors affecting organic reactions. The main factors are inductive effect, mesomeric effect, reactivity of lone pair, and steric hindrance. Inductive effect is an electronic effect due to polarization of sigma bond within a molecule or ion. It is due to electronegativity difference between the bonded atoms. The more electronegative atom pulls electron in the bond towards itself, creating some bond polarity. See this haloalkane, whereby the chloride become partial negative and the carbon attached to chlorine become partial positive due to electronegativity difference. There are two types of inductive effect: negative inductive effect and positive inductive effect. Negative inductive effect. A group is said to exert negative inductive effect if it withdraws electrons away from carbon or functional group. Most electronegative atoms than carbon withdraw electrons away. See this haloalkane, whereby electrons are withdrawn by the chlorine due to electronegative difference, and the direction of arrow shows the direction of electron. Negative inductive effect increase acidic strength of carboxylic acid. Carboxylic acid is the strongest acid amongst organic compounds. Its acidic strength is increased when most electronegative atom, halogen X, is attached to it. Example: 2-chloroethanoic acid is more acidic than ethanoic acid. Halogen attached to carboxylic acid tend to withdraw electrons away from the carboxylic group and consequently reduce the electron density of the OH bond. This makes OH bond weak, easy to break. Consider this compound, whereby chlorine withdraw electron away from the carboxylic group. In an aqueous solution, OH bond breaks readily and releases hydrogen ion easily and hence more acidic. The inductive effect is stronger as the halogen becomes attached closer to the carboxylic group. Positive inductive effect. A group is said to exert positive inductive effect if it releases electrons toward carbon or functional group. See this structure of carboxylic acid, whereby the alkyl group releases electron to the carboxylic group functional group. R equals to alkyl group. Few groups exert positive inductive effect. The only group that can release electron is alkyl group. The electron releasing ability of alkyl group increases as alkyl group grows bigger. Some influences of positive inductive effect. Positive inductive effect decreases acidic strength of carboxylic acid. See this structure of carboxylic acid, whereby the alkyl group releases electron toward the carboxylic acid. Due to positive inductive effect, electron density at OH bond increases. OH bond becomes stronger and difficult to break, hence acidity decrease. Positive inductive effect increases basic strength of amine. Amine is the strongest base among organic compounds. Its basic character is due to presence of lone pair. So the basic strength of amine depends on reactivity of lone pair. Consider this reaction between amine and hydrogen ion. Due to alkyl group, the lone pair from the amine will be repelled away and make readily to react with hydrogen ion. Any group that releases electrons towards N will increase reactivity of the lone pair. The coming electron from the electron releasing group, alkyl group, repels lone pair away from N and hence make them closely attached and more reactive. This makes them more available to associate with hydrogen ion. Increase in reactivity of lone pair increase the basic strength of amines. Note: negative inductive effect decrease basic strength of amines. Number 2. Mesomeric effect. Mesomerism or resonance is the movement of a whole electron pair from one place to another and back again to its original position. Mesomeric effect is the effect which is caused by movement of electron pair from one place to another and back to its original position. Electrons involved in mesomeric effect are pi bond, lone pair, and net negative charge electron pair. Note: sigma bond cannot be involved in mesomeric movement. Why? Because if sigma bond is involved in mesomerism, will result into cleavage of molecule, hence destroy the compound. Condition for mesomerism or resonance to occur: conjugation. Conjugation system is a system of alternation of sigma bond and pi bond. See this structure whereby carbon alternate themselves with double bond and single bond. Also, see this structure of benzene where there is alternation of double bond and single bond, which are pi bond and sigma bond. Number 2. Carbon contain pi bond and attached to an element which have a lone pair. See this diagram whereby carbon is attached to double bond and an element M with lone pair. This reaction shows example of compound that undergoes mesomerism. Example: carboxylic acid. Number 3. Carbon which have pi bond and attached to an element which have negative charge. See this diagram. Carbon is attached to an element with pi bond and another element which have negative charge. Also, this diagram shows the example of mesomerism which take place in carboxylate ion. Effects of mesomerism and delocalization on pi bond electron pair. Important to know. Pi bond is unstable, easy to break it, and chemical reactive. Compounds with pi bond are a good source of electrons, hence nucleophiles. This is true only when pi bond is fixed or localized at just one site. If pi bond is involved in mesomerism and delocalization, it becomes strong, stable, and chemical inactive. Generally, mesomerism has the effect of increasing strength and stability of pi bond electron pair and hence reduce their reactivity. This diagram shows the reaction between alkene and hydrogen and platinum to form alkene, and the reaction between benzene and hydrogen under platinum where the reaction is not possible to occur. This can be justified by considering the pi bonds in alkenes and benzene. Alkene and benzene are similar because they are both unsaturated hydrocarbons. Their only difference is that the pi bond of alkene is localized, making it very unstable and reactive, while the pi bond of benzene is delocalized, making it very stable and unreactive. At room temperature and pressure, the pi bond in alkene can easily break and undergoes addition reaction. This reaction shows that alkene plus electrophile nucleophile can undergo addition reaction. In case of benzene at room condition, benzene instead of undergoing electrophilic addition reaction as expected like in alkene, it undergoes electrophilic substitution reaction whereby the side hydrogen is replaced by the incoming electrophile. The pi bond in benzene does not participate in this reaction. This is because the pi bond is very stable since it involved in mesomerism. This reaction between benzene and electrophile nucleophile shows that benzene undergoes electrophilic substitution reaction instead of electrophilic addition reaction. Other compounds that are having pi bonds but don't react by using pi bond electron pairs are acyl chloride and amide. These compounds are expected to undergo addition reaction, but instead substitution reaction takes place. Effects of mesomerism and delocalization of net negative charge electron pair. Mesomerism and delocalization result into the compound concerned to be acid. Consider a carboxylic acid. Mesomerisms take place in carboxylate ion. Carboxylic acid dissociates in water to form carboxylate ion and hydrogen ion. This resonance structure shows the mesomerism of carboxylate ion. After delocalization, a hybrid structure is formed which shows the direction of movement of the electrons. Study question. Explain with reason why phenols are acidic in nature while alcohol are basic in nature despite the fact that both have the same functional group OH group. Solution. Phenols can undergo mesomerism when it is in phenoxide ion, while alcohols do not undergo mesomerism. That's why phenols are acidic. Consider the reaction below. Phenol dissociate to form phenoxide ion and hydrogen ion. This resonance structure shows how phenoxide ion undergoes mesomerisms, which led to electron density of the OH group to be low, hence hydrogen can be released easily. Hence phenol become acidic rather than basic in nature. After delocalization, hybrid structure is formed, which shows the direction of electron in the phenoxide ion.